Okay. Okay. So it's clear, right, what the definition is. It's just we're just simply drawing these analogies with the numbers, but as we'll see, the inverses behave differently here. So let's go back to the original 2714. And suppose I want to compute the inverse of 2714. So the question is, what matrix, and it's going to be a 2 by 2 matrix, when multiplied by this, either from the left or from the right, but that's the way I wrote down here, so let's stick with this, will give me, on the other end, an identity matrix. This is what we want to do. Now, let's for a second return to that system of equations that had a unique solution. And let me now put a B on the right-hand side, because just to let you know where I'm going with this, is that what I want to say is that AX equals B, where B is a non-zero vector, will have a unique solution. We'll have a unique solution. So let me just indulge me, let me do these examples for now, and then I'll give you precise definitions a little bit later. So to answer this question, so this is our under question mark, what I'd like to do is solve the system of equations, like something like 2x1, let's pick B, concrete B. Let B be something that's easy to deal with. So let me write down the system of equations. 7x2, let me make this 9. So that 1, 1 will be a solution. So I'm picking easy numbers, just for starters, for the first example. 4x2, that's going to be 5. I think everybody can see that this, so what's the solution to the system?
1, 1.
Yeah, as solution 1, 1. That is x1 equals 1, x2 equals 1. That is A times 1, 1. 2, 7, 1, 4, 1, 1 will give me exactly 9, 5. A hand-picked right-hand side so that the solution is easy to see. Now, if I'm to find an inverse of this matrix, this inverse is going to be such. This is what we're looking for. That when I multiply it by 9, 5, I should get the original 1, 1 back. Does this make sense? Like in terms of the analogy with the numbers, for example, right? So I'm looking for something that A takes my 1, 1 vector to 9, 5, right? So A takes my 1, 1 vector to 9, 5, and then now I'm looking to undo the action of A. Now I want to find some matrix that when multiplied by 9, 5 will give me the 1, 1 vector. Okay, so let me first give an answer and then see how to compute it. Answer. A minus 1. And what would be the answer to this? Okay, so somebody remembers those formulas? Do I have this right? Okay, I'll show you the formula in a second. Okay, so, okay, let me show you a formula that I'm very reluctant to rely upon, but I tell you. So if you have A, B, C, D matrix, if A is that, then A inverse is 1 over AD minus BC. This is a quantity that we'll later call something. It's called a determinant, but for now, it doesn't matter. And then what I do is I change the entries of the matrix this way. Like this. Okay. So what I did is I switched the entries on the diagonal, and the entries off the diagonal I flipped the signs off. Now this is completely artificial. I'm reluctant to even write this down because it's completely unclear where does this thing come from. There's some formula, you plug in, then you get the inverse. Okay. So this is how I computed this right now. It's like when I'm telling you this is the inverse. Okay, so someone in the back of their mind may have some kind of like strange formula. And here, well, I just plugged it in. These numbers were 4, minus 7, minus 1, 2. I flipped them, or rather, the numbers were these guys. So I plugged it into the formula. So it's clear, I think. The A, B, C, D were 2, 7, 1, and 4, respectively, right? So this is my original A. here. Okay, so that's fine. So now, first of all, let's check that this is the inverse. Does this matrix that we just wrote down out of the blue, let's pull out of the hat, is this the inverse? So check. Indeed, 2, 7, 1, 4. If you multiply it by 4 minus 7, so help me real quick. Multiply those matrices, and let's make the right-hand side purple. It's going to, I want this to be an identity matrix. This is under question as of right now, but let's see. 2 times 4 plus 7 times minus 1. Is that a 1 here? That's a 1. 2 times minus 7 plus 7 times 2. That's a 0. That goes there. And so on. Okay, so let's do it. 1 times 4 minus 4 times 1. Get a 0 there. And you get the idea. 1 times minus 7 plus 4 times 2 minus 7 plus 8. That will give me a 1. And that indeed works out to be the identity matrix. And in fact, if you multiply it the other way around, you get exactly the same result. 2, 7, 1, 4. And you will get exactly the same result. Okay, so it's going to be the same identity matrix. Any way you do it. From the right, from the left, or from the right. Now, let's do a couple more examples, and we'll be on our way. Some matrices are easy to invert just by thinking about what they actually do, what their effect is, without doing any computation. So let's do a couple of those first, and then we'll move on. Just by thinking of what they do, what their action is, what they do. Example. What is the inverse? What does this matrix do? Let me do this one first. It's easier. What is the effect of this matrix? I'm going to call this matrix P, by the way. What does this matrix do when you multiply it by some matrix A? It doesn't matter what that matrix is. Let's make it 2, 3, 7, 1. Again, numbers are out of the blue. What does P do to it?
Does it flip? Does it flip the...
Flips the rows. So the answer is going to be 7, 1, 2, 3, right? That's going to be the answer. Let's call this some matrix B, flipped A. So what would undo this operation? That is, what matrix, when multiplied by B, will get me the original matrix A?
The same, P.
The same matrix. So does it stand to intuition that the inverse of P has to be, then P inverse has to equal P, right? Because I applied P to some matrix, it flipped the rows. When I applied that P to the matrix that came out on the other side, I flipped the rows again. So I had to get back to the original matrix. So P inverse must be itself. Let's check. 0, 1, 1, 0, multiply 0, 1, 1, 0. And by the way, this all generalizes to bigger matrices. If you multiply those two, you get exactly the identity matrix. So that works out, right? Nobody doubts that. Example 2. How about this matrix? Let me do it this way. And let me call this E. For it. And there is a point, I promise you, there is a point to all of this. These are just nice small examples, but we'll use all these examples in what's coming. Because I want to justify to you the so-called Gauss-Jordan elimination procedure that computes the inverse of a matrix. No determinants or anything today, for now. So let's take this matrix, E. Okay, what does it do? So that means you multiply E by some matrix. 1, 2, 3, 4. What's the effect?
So isn't it what we said that it multiplies the second row and it adds to the first?
Yes, yes, that's exactly right. So and notice I'm multiplying this from the left. This guy, please notice that this stands on the left. And when this guy, this elementary matrix, stands on the left, it manipulates the rows of the blue matrix. So if you do the multiplication, you will see that, first of all, the bottom row stays the same if you just do the usual multiplication. And the top row becomes top row plus twice the second row. So what happens to this is that this becomes a 7 and this becomes a 10, right? When you multiply those matrices together, right? Does that make sense? Now, what is undo E? What is undo E? Will give us the inverse of E. The undo operation will give us the inverse of E. Again, we're avoiding computations just by thinking about the effects of these matrices. It's the only way we're computing the inverses. So I'm taking some matrix. In this case, that some matrix is A, B, C, D matrix. So here, 1, 2, 3, 4. And E does to that matrix, what E does to that matrix is add twice the second row to the first row. How would I get back the original matrix? That is, how would I get back what E minus 1 multiplies the purple matrix now to get back the blue matrix, which was 1, 2, 3, 4. So I want to, what should I do to this purple matrix to undo the operation? And once I figure this out, then whatever sits in this matrix has to be the inverse of this. So how about if I subtract twice row 2 from the first? So help me out. So what I did is
1 minus 2, 0, 1.
Yes, exactly right. But I just want to make sure everybody sees this. So I've added twice row 2 to the first row. Now, if I subtract twice row 2 from the first row, then I'll get the original matrix back. And the matrix that does the following: subtract row 2 from row 1 is going to be this matrix. Do people see this? Okay, so 1 minus 2, 0, 1 is the inverse of 1, 2, 0, 1. So some inverses are easy to compute just by thinking of what their entries are. Okay, one quick one. This is like a 2-second one. What's the inverse of this? What's the effect of this matrix? Let's call this F or something. The effect of this matrix, it's almost an identity. It just has one of those ones. This would be an identity if I didn't have this minus 1 here. This minus 1, what's the effect of this? Is to multiply the second row of whatever matrix I have on this side, to multiply the second row by just flip the sign of everything in that row. If I flip that sign back again, I should get the original matrix back, right? So the answer is that this is the inverse. So again, this is another example of a matrix that is its own inverse, right? So if you multiply those two matrices together, do the usual matrix multiplication, you would get the identity matrix back as a result, right? Are we good with this? Now, finally, to the point. So key point. Every row operation corresponds to multiplying by one of those elementary matrices. And I'll start with an example. That's after, at the end of this, we'll have the inverse of this matrix. Okay, by an elementary matrix, multiplying by an elementary matrix. Well, again, the only elementary matrices are the ones that we just talked about. This guy that flips some sign, this guy that adds a multiple of one row to another row, and this guy that flips the rows. These are our three allowed elementary operations. Now, here's what I want to do. I want to start here and now do Gaussian elimination on this matrix so that at the end, I get the identity matrix. So I want to end up, so we're doing nothing new other than doing row reductions, only this time we're actually writing down those matrices, elementary matrices, that correspond to the elementary row operations. Okay, want to get to I, which is this. Okay, so how about step one steps? How about first, let's flip the row. So I have this nice 1 here on the top. So to get to 2, 7 here and 1, 4 here. Okay, flip the rows, flip rows. I multiplied by this elementary matrix. Let's make these guys blue. And I'm going to call this P. And this will be my original A. So I'm multiplying P by A. What's the guy that flips the rows? Was it this guy? Well, I should. This is what I want to do. Multiplied by the original matrix A, 2, 7, 1, 4, to get this. Everybody agree that we have that? Now, step number 2. Subtract twice row 1 from row 2. What's the elementary matrix that does that? I have my PA from the previous step, which is 1, 4, 2, 7. The guy that I got on the previous step goes here. And I'm multiplying this guy by some matrix that does that. What will that be? What will that be? Where do I get to? What is the matrix that puts a 0 here, doesn't change the first row, puts a 0 there, and then -1 there? What matrix? Let's call this E. Let's make the E blue. What blue E multiplies this matrix for me to get that? Help me out, please.
1, 0, 2, 0.
1
minus 2, 0.
Okay, so I want to subtract row 1 twice row 1 minus 2 row 1 minus 2 row 1 minus 2 row 1. Now it's correct, right?
Yep.
Okay, so now I start with 0 minus 1, 0 minus 1 here. That's my matrix from the previous step, EPA. And I'm multiplying this by some matrix here on the left side. That actually F is a good name because it flips the signs. I just want to flip the signs. So what's this matrix here? That when multiplied, okay, let me actually write down the answer here so I have less to write. I want to get to this matrix. What's the result? Thing matrix. Will this work? It just multiplies the second row by -1, right? So now I have my F EPA here from the previous steps. So I just started with A, and then I'm multiplying by these elementary matrices on the left. The fourth and the final step would be to start with this EPA, FEPA, which is 1, 4, 0, 1, and finally get to the identity matrix. Let's make that purple because that's the final step. I want to make this an identity. How do I make this into an identity? By multiplying by what? I'm not changing the second row, but the first row, what I'm doing is I'm subtracting 4 times, okay, row 1 minus 4 times row 2, right? And I get to the identity matrix. Do people agree? So let's call this matrix G. So the result, G, F, E, and by the way, for a computer program to multiply these elementary matrices, it's a cinch. Yes, we're doing a 2x2 example, but if it's like 1,000 by 1,000, these matrices have a bunch of zeros in them, just a couple of ones here and there on the main diagonal, and then maybe some sign is flipped somewhere or some entry is a non-zero, just one other entry. So to multiply those matrices is very quick. So now we want to finally get to the main point. My point today is that this matrix here, key point, G in this example, F, E, P product is a inverse, right? Because I got to the identity matrix when I multiplied A on the left by a sequence of these elementary matrices. So this has got to be, okay, got to be A inverse. Do people see that it has to be? We'll check this in a second. So I'm taking A, and I'm doing elementary row operations to this A so that at the end, I end up with an identity matrix. So whatever I did to A, each row operation corresponded to multiplying that original A by some elementary matrix. So when I take that on the left, the matrices that accumulate on the left, and I consider their product, G, E, F, and P, let's write this down. Check. Let's make the check blue because our matrices were blue. So we started with a P, that was this guy. Then this is where we were about to make a mistake if you didn't stop me. -1, 0, 0, 1. Then I flipped the sign, right? So I think we had this. And then finally, we had our matrix G here, which was 1 minus 4, 0, 1. So this was our P, this was our E, this was our F. Okay. Now my claim is that when I multiply those matrices, is no longer going to be magic. When I multiply those matrices, I better get that inverse that we wrote down in the beginning according to some formula about the determinants or whatever it was. So let's do this. This is quick. This should take us a second. So this equals, what's the product of these? So let me rewrite those matrices first. 0, 1. So I have my G and F here. I'm just rewriting those. Okay. And what do I have here? What does this do? Can you give an answer without computing anything?
It leaves row 1 as it is. And then from row 2, it subtracts 2 times row 1.
That's correct. You can think of it that way, but can you notice one more thing? I'd like to draw people's attention to this. It actually flips the answer would be this, 1 minus 2, right? You would get the same answer by what you said, right? But why am I, it's not like I'm making a big deal out of it. What I want to draw people's attention to is that, yes, we said this matrix flipped the rows, but it flipped the rows when we multiplied A from the left by it. When I'm taking some matrix and I'm multiplying it by this P from the right, it has the effect of flipping the columns of that matrix. Do people see this? Okay, so now let's continue. It's not too much to compute. What does that do? So help me out without computing anything. What should that matrix do, please? It doesn't
be the same. And
this one, it just multiplies by -1, this row, right? Okay. And finally, What's the result of that? Let's compute this one now. 1 times 0 minus 4 times minus 1. Is that a 4? 1 times 1 minus 4 times 2. Is that a minus 7? So help me out on this one. 0 times 0 plus 1 times minus 1.
You get a -1.
-1 and
2.
And 2. Now, this matrix better be the inverse. My claim is that this matrix is the inverse of A. We started with this A. Okay. So what was the inverse that we wrote down? Now we wrote so much that, okay, let me rewrite the original A. We have an inverse here somewhere when we, okay, there we go. Is this matrix that I just got, is it the same as what we computed according to some formula? Right? Do we get the same? Okay, so we got the same. So the point, finally the point, took a while to make the point. I can't believe, what time is it? Okay. The product of those elementary matrices that bring the original A to the identity matrix is the inverse of the original matrix. That's the Gauss-Jordan idea of computing the inverse. Now, if you're given a problem like this on the test, you don't write let me now show you how you actually write this down, okay? So this was the entire thing was to make the point. But now to actually compute it, you do the following. You write down the original system, the original A, which is 2714. Okay, way to do it. You take the original matrix, which is 2714, if I'm not mistaken. Was it 2714? And you add to it, on this side, the identity matrix, like this. And you encapsulate all these operations, the elementary row operations, by manipulating the rows of this augmented matrix, right? And what will happen is that I'm going to manipulate these rows somehow. And at the end of the day, I will end up with something like this. Here, I'm going to end up with an identity matrix. And here, I'm going to end up with something. That something is going to be inverse of A. The inverse of 2714. So let's do this. It's actually pretty quick. Unless there are some fractions that come up, which, if you make an arithmetical mistake somewhere, then, so kind of have to be careful. But this one is a simple example, so it should be good with this. So let's take a look.
Half the first row?
Sorry?
Should you half the first row?
Yes, we can half the first row. That's possible, but we want to avoid fractions. For that reason, let's just flip the rows. Right? Can we flip the rows? That's easy. That doesn't change anything. Yeah, let's just do that. So that just you could have it and you'll get the same result. But then you would have to deal with the fractions, then come back, multiply again by 2. You'll end up with the same result. But if we do it like this, 1, 4, 0, 1, 1, 0 here is 2, 7. That's the first step. Okay, so flip the rows. Flip rows. The next step. What's the next step?
Subtract 2 times row 1 from row 2.
Subtract 2 times row 1 from row 2. So you leave the first row as it is and subtract 2 times row 1 from row 2. Do I get this? Okay, and then we continue. Okay, so this is row 1, 2 minus 2 times row 1. Then we continue. What do I do here? Can multiply by -1 if we want to, although, okay, let's multiply it by -1. So I get a 1 there. So I have a -1, 2, 0, 1. And here I have 1, 4. Mult row 2 by -1. Okay, then subtract 4 times row 2 from row 1. And you get, finally, the identity matrix here. Let's make that purple. Okay, let's make this, let's just stick with these colors. And what do I get? do I get this? So help me out. What was the answer? Minus 4 times row 2. Okay. Do I get this?
Professor,
Yeah.
when you subtract 4 times row 2 from row 1, the first element in the second matrix, if I can say it like that, shouldn't be like 4, not 1. It's 4
yeah, so
times, it's minus 4 times minus 1.
4 times, yeah, I should get that 4. So yeah. So when you subtract 4 times this row, oh yeah, row 2, you get a 4. Exactly. Yeah, so now we're consistent with that. So I was worried we didn't get the same answer, but of course we'll get the same answer. So now this is my identity matrix here. This is our identity matrix here. And this is A inverse is sitting here. So notice we started with A and identity here. We did these steps. This is the way to write it down. This is the Gauss-Jordan elimination way of finding the inverse. And once you get to the identity matrix here on this side, you'll end up with the inverse of A on the other side. Does that make sense? So that's the procedure. Real quick, here's an example of a 3x3 matrix here somewhere. Does exactly that. Okay. Okay, so here's a 3x3 example. Starts with this matrix and does nothing new, absolutely. Does the Gauss-Jordan elimination. It proceeds in 2 phases. First, you bring this matrix to the upper triangular matrix. I guess call it phase 1, although we didn't separate those phases in the small example. Okay, so let's see how it's done real quick. So how do I make a 0 here? Row 2 minus twice row 1. Puts a 0 there. You do this to the entire augmented matrix. So the first step gets the 0 there. Now I want to make a 0 here. How do I do it? I add row 1 and row 2. Row 1 and row 3. Here's row 1 plus row 3. Puts a 0 there. And you get the idea. How do I make a 0 here? Well, add row 2 and row 3. Puts a 0 there. And now you have an upper triangular matrix. Something is done to this other matrix on this other side. That whatever ends up in this piece will be the inverse. So now, while we do not have an identity matrix here on the left side, we keep doing it. So now we have to make zeros up there. So in the second phase, you start making those zeros up there. So how do I make a 0 there? You add twice row 3 to row 2, twice row 3 to row 2, and that will put a 0 there, right? So that's that 0, and so on. So you keep on doing this until you get those zeros at the top, like above the diagonal. And then you can scale these rows, finally. Here is, like, I guess it's a slightly more involved example because those fractions show up, right? So, but at the end of the day, you end up with some matrix in this right-hand side piece of the augmented matrix. And then whatever ends up in the right-hand side has got to be the inverse of A. This is how we'll do the inverses. So now the main point here is understanding why the product of elementary matrices will produce the inverse of the matrix. But I think it makes sense now, right? With a small example that we just did. Okay, so now this was like today was unfortunately just mechanical. It's all like numbers. Maybe it's not that exciting, right? But that's something that has to be done. So we had to do this today, right? Ideally, we'd do more interesting things. Like we talked about the inverse. Now we could actually do mathematics by proving things like, well, what guarantees that the inverse is unique? Why is the inverse unique? Okay, we claim that the inverse is unique. If it exists, it's unique. We want to prove that fact. Okay, so I think we can end today, right? Do people have any questions?